Now we'll wrap up chapter 1 with section 1.4 on circles. So this is a little briefer, especially than the previous section we did. And in this section, we write the standard form of the equation of a circle, graph circles, and work with the general form, though not very much, of the equation of a circle. So a definition: a circle is a set of points in the Cartesian plane, the xy plane, that are a fixed distance r from a fixed point h comma k. The fixed distance r is called the radius, and the point hk is called the center of the circle. So graphically, this is what we get. Center is hk. All points a distance r from that center point produces a circle. We've got a formula for distance, and from that distance formula, we'll derive the various versions of the equation of a circle. If xy is a point on the circle, as given in the picture above, we've labeled this point here xy, the idea being x and y can vary as long as the point stays on the circle. So we want to find an equation that relates x and y and h and k. So if xy is a point on the circle, as given in that image, then the distance from xy to hk is r, because that's the definition of a circle. From the distance formula, we get distance from h to k, sort of a x2 minus x1 squared kind of thing. Here is an x value, here's an x value. So we'll take the difference of these two, say x minus h squared, difference in y coordinates, y minus k squared, square root of, we want that to equal r. Notice r is non-negative because it's a distance. In fact, being a distance, we'll treat it as positive. We don't deal with circles of radius 0. So if we square both sides and observe that r is strictly greater than 0, that is, r is positive, then we can lose a square root. We'll get this equation. And also, we do not introduce any extraneous roots. We didn't introduce any new information. It's possible, not in the setting of circles, but one side or the other, we could have a negative sign in it. There could be a negative sign over here implying r is negative. We know that's not the case, though. We could have a negative in front of the r. In that case, r itself would have to be negative, so the right-hand side is positive. That's not the case either. We know exactly r is greater than 0. Squaring both sides introduces no information, as long as we remain cognizant of the fact that r is greater than 0. So this gives us the relationship between the coordinates x, y of a point on the circle, the center of the circle, h comma k, and the radius of the circle, r, greater than 0. And this is called a standard form of an equation of a circle with radius r being understood to be positive, and center hk. Standard form, as given here, we'll illustrate that with a few examples. If the center happens to be 0, 0, let's call special attention to that case. The standard form of an equation of a circle of radius r with center at 0, 0 is x squared plus y squared equals r squared, h and k both being 0 and disappearing. So a little observation there. When you deal with trigonometry, the standard form of a unit circle centered at the origin will be important. X squared plus y squared equals 1 will play a big role when you deal with the trig functions, sines and cosines and so forth. Not our problem in Precalculus 1. Big problem in Precalculus 2, though. If r equals 1 and the center is the origin, then we get the unit circle, as it's called, x squared plus y squared equals 1. Circle centered at the origin with radius 1. And of course, it looks like that. Again, not playing a particularly important role in what we're about to do, but playing a very important role in some things you'll do later. Let's look at 3 examples illustrating the standard form for the equation of a circle. As I observe, we'll have something called a general form as well. It's the standard form that's the best form. I can look at the equation, I can tell you the center, and I can probably tell you the radius as well. So some nuances on being given particular types of information. In number 18, you're told to write the standard form for the equation of a circle with radius 4 and center hk equals 2, -3 and graph it. Okay, the only important parameters for a circle are the radius and the center, so not a problem. Standard form of the equation of a circle is x minus h, quantity squared, y minus k, quantity squared, equals r squared, saying quantity to indicate the parentheses. So my verbal version of the symbols. In this case, we've got hk equals 2, -3. So we'll put a 2 in for h. There it is. We'll put a -3 in for k. There it is. Be mindful of the subtraction of a negative. So make sure you use parentheses and keep an eye on that. Right-hand side, radius was 4, so we get 4 squared. Simplifying, and the only thing to simplify is the y minus -3 gives us this. I guess we can square the 4 if you like. It gives us 16. And so we get x minus 2, quantity squared, plus y plus 3, quantity squared equals 16. To graph the circle, we know the center is 2, -3, so let's go to the point 2, -3. There's the center of the circle. We know the radius is 4. So in practice, let's find some points on the circle, distance 4 from the center. Let's go 4 units straight up. By the way, that leaves us at the point 2, 1, which you could confirm satisfies this equation. 4 units down, 4 units to the left, and 4 units to the right, and we could find the coordinates of those points quite easily. But if I were me, I'd plot those 4 points. They're at the top and the bottom and the left and the right of the circle, and then kind of flesh it out based on those points. So radius 4, plotting some points. Of course, you have to draw this by hand in practice. I would introduce those 4 points. They're easy to find in this example for sure. And based on those, sketch out the circle. Let's do another one. So let's see, in this case, we were given radius and center. The next one, we're given the equation and asked to find the radius in the center and intercepts and graph. So quite similar to what we just did, except now we're starting with the equation instead of starting with that other information. Standard form is given here, so we'll match this with what's given, seeing what subtracted from x and then squared, nothing. H must be 0. What's subtracted from y and then squared? 1. K must be 1. So the point HK must be 0, 1, and that must be the center of the circle. The radius, this must be the radius squared. So we have r squared equals 1. So r itself is the square root of 1, also 1, of course. So the radius is 1. If we're going to graph it, this is the information we're likely to use. We'll go to the point 0, 1 and go 1 unit up and down, left and right from that to find extreme points on the circle and then sketch it based on that. They also wanted intercepts. Okay. For the x-intercept, we'll set y equal to 0 as previously done in the original equation. Set y equal to 0 will produce x squared plus 0 minus 1 quantity squared equals 1. That's x squared plus -1 squared, x squared plus 1 equals 1. Subtract 1 from both sides, we get x squared equals 0. So x must be 0 when x is 0. And we were given y 0, and we set y equal to 0. We get the point 0, 0 as the x-intercept. So the x-intercept is the origin. You might think for a second. So we got a circle that touches the x-axis, or crosses it, in only one point. I mean, it couldn't cross it if it's a circle. This circle must be either setting right on top of the x-axis, or it must be below the x-axis and have the x-axis tangent to it at its highest point. We'll be able to distinguish that from the other information. But the fact that we got only one x-intercept for this circle implies a certain geometric behavior of where the circle is. as we'll see when we graph it. For the y-intercept, we'll set x equal to 0 in the original equation. Put a 0 here, producing 0 squared plus y minus 1, quantity squared equals 1. Drop that, leaves us with this. Let's take a square root of both sides. Dealt with as appropriate. When you take the square to the left side, square root of something squared is the absolute value of the something. Right-hand side is the square root of 1, which is 1. But we do have this absolute value introduced right here, telling us y minus 1 equals either 1 or negative 1, equals plus or minus 1. This is the first time we've dealt with an equation in that form, I think. Maybe back when we dealt with the quadratic equation, we use these symbols. Adding 1 to both sides, we get y equals 1 plus or minus 1. That is, y equals 0 or 2. So we get the y-intercepts of 0 or 2 for the y values expressed as a point, as this book does the intercepts. That's 0, 0 and 0, 2. We set x equal to 0 to find these values. So here's what we've got. A circle of known center, known radius, and we got 3 points on that circle, allowing us to produce this. There's the center, and we knew the radius was 1. I mean, that's enough information right there. Go 1 unit to the left and right, 1 unit above and below. I'm using the same scale I've used in all our graphs, kind of a 0 through 6 or 7 in each direction. But we'll start with the center, go up and down and left and right. Just a quick little comment. The center itself is not a point on the circle. The circle's the stuff outside, though I do plot the center because it's a useful point, but not a point on the circle. And what was it? We had the X-intercept was 0, 0. Oh, that's why there's only one X-intercept. It's just sitting there on top of the X-axis. It has the X-axis as a line tangent to the circle. And there's 2 y-intercepts, 0, 0 and 0, 2. So the top and the bottom are the intercepts with the y-axis. The bottom point is the intercept with the x-axis. And all the geometry makes sense. And you might see, if we go looking for intercepts, then we're either going to have 2 intercepts, 2 x-intercepts, or 2 y-intercepts with these circles, or none, in which case the circle might be sitting somewhere out here, or we'll have this tangent behavior. We'll have 1 intercept. If that's the case, then it must be that the circle is tangent to that axis, and we get a behavior something like this. Another one to illustrate these ideas. Here's an equation. It says of a circle, doesn't look like circles, not in standard form at least. Find the center, radius, intercepts, and graph it. So same instructions as in the previous example, but the equation's a bit messier. All right, let's put it in general form. No, I'm sorry, in standard form. Let's take the original equation, let's divide by 3. Divide both sides by 3. This 3 divides out, this 3 divides out. Negative 12 divided by 3 produces a negative 4, so equivalent equation. We're going to have to complete the square. We want this to read x minus something squared plus y minus something squared equals something else squared. The x stuff, we're good. We got x squared. Or if you like, x minus 0 squared. This, we've got somehow to absorb this y inside a squaring. Let's complete the square. As we did in Appendix A3, the section on polynomials, there's a hyperlink to it built into the online notes. And what we need to do then is treat this parameter, I think we called it b in section A3. We'll take b divided by 2 and square it. We need to add this coefficient divided by 2 squared to both sides. Add this to both sides. Can't argue with the validity of it because we just added negative 4 divided by 2 squared to both sides. By the way, negative 4 divided by 2 is negative 2. Square it. It's just 4. We've just added 4 to both sides, giving us x squared plus y squared minus 4y, that's before plus 4, equals 4. And we just added 4 to both sides. Why 4? I guarantee you, this is factors is a perfect square. And we need a perfect square to have the standard form of a circle. In fact, this is y minus 2 squared. You see, if you're good at factoring, that this factors into y minus 2 squared. If you go back and look at the formula involved in completing the square, this is y minus b over 2. The b over 2 stuff, the stuff inside the parentheses here is negative 2, and sure enough, we've got a negative 2 right there. So y plus negative 2 squared. So the completing the square formula tells you exactly what you'll get. So whatever works for you. This I like. This is standard form. So the standard form shows us that we've got x minus h quantity squared. H must be 0. H is 0. We got y minus 2, y minus k squared. K must be positive 2, right? Remember, it's y minus k. So we're getting k is positive 2 here. And the radius squared is 4, so the radius itself must be 2. We've got r squared on the right-hand side, if you like. R equals 2. Knowing r squared is 4 introduces the possibility that r might be negative 2. But remember, the radius is never negative. So we always take positive square roots in this stuff. The radius is 2. So they wanted the center and radius. There it is. They want the intercepts. All right, to find the x-intercept, we'll set y equal to 0. Not sure which of these you want to set y equal to 0 in. I've written it up where I went back to this equation, it looks like. I can use the original equation. I can use this equation. We can use the standard form. They're all equivalent. So plug y equals 0 into one of those. Looks like I've typed this up in such a way that I've chosen that one. So we'll have x squared plus 0 squared minus 4 times 0 equals 0, producing exactly this. It simplifies, and that's probably the easiest one to use with the arithmetic, simplifies to x squared equals 0, so x equals 0. So when y equals 0, x equals 0, and the x-intercept is 0, 0, just like we had in the previous one. A coincidence. For the y-intercepts, we'll set x equal to 0. Okay, if you do that in this version of the equation, that'll produce 0 squared plus y squared minus 4y equals 0. Right, we just plug 0 in right there. Got the other stuff remaining. Or y squared minus 4y equals 0. Let's factor it. Factor a y out. Y times y minus 4 equals 0. So y equals 0 or 4. And then the y-intercepts are x equals 0, y equals 0, 0, 0. Or x equals 0, y equals 4, the 0.04. All right. So we found everything except for the graph. How you want to graph it? Well, we've got some points on it. Probably I want to take the center and just go 2 units to the left and the right and above and below. That's the easiest way. In fact, doing that, I suspect, produces some of these points. Here's the center, 0, 2. The radius was 2. So we go 2 units left and right, 2 units above and below, if you like. That produces useful points to sketch out the circle. What were the intercepts? 0, 0 was the x-intercept. Oh, we got a circle that's tangent to the x-axis again. That's why there's only one, or exactly one, x-intercept. And the y-intercepts were 0, 0, and 0, 4. So we've got the correct intercepts. In fact, they're the extremes on this. We've got the correct center, and we've got the correct radius. That's the graph of the circle. Don't go plotting a whole bunch of arbitrary points. That'll be really hard with the circle because it's not a function. Violates the vertical line test. So not a function. You'll be lucky if you can find points to plot. The way to deal with it is this more subtle way of finding the center and the radius. Based on that, maybe plot some points. Go to the center, go left and right. The radius, that'll produce you 2 points. Go up and down, that'll produce you 2 points. That gives you 4 points on the circle. Not just any 4 points. It's the highest and lowest point, the leftmost and the rightmost point on that circle. You don't graph things just by randomly plotting points. You probably plot points, but you plot special points. And you know why they're special. What makes them special here? Uppermost, lowermost, leftmost, rightmost points on a circle. You know it's a circle, you know the shape, and you know from those extreme points based on the center and radius, the extent of the circle, the region in which it lies. Back to the notes. If we multiply the standard form of the circle out, we get an equation of this form. You'll have an x squared term and a y squared term. You'll have an x term, a y term, and a constant term. Standard form given up here. Foil this out, foil this out. This will produce an x squared minus 2xh plus h squared. This will produce y squared minus 2ky plus k squared. Maybe bring the r squared to the left-hand side. You had an x term, you had an x squared term, you had a y term, a y squared term, and you had a bunch of constant terms. The constant terms can be combined and brought to the left-hand side of the equation to produce something like this. All right, so circles can be written in this form. I don't like this form. I like the standard form because I can see what the center and radius are from that. I can't from this. Not all equations of this form represent circles. If we were to take a, b, and c equal to 0, this would disappear and give us x squared plus y squared equals 0. Well, that would only be satisfied when x and y are both 0. And we get a radius of 0, and that doesn't count as a circle. Some people would count it as what's called a degenerate circle, but we're not treating single points as if they were circles of radius 0. It's just not the verbiage we're using. You might see different verbiage in other places. So beware, just because you have an equation with some x squares, y squares, x, y's, and constants in it doesn't mean it represents a circle. When you have something of this form, it represents a circle of center hk and radius r. So develop a fondness for the standard form, not for this other stuff. When it's a graph of the circle, so we're assuming this actually is a graph of a circle, this equation, x squared plus y squared plus ax plus by plus c equals 0, is called the general form of the equation of a circle. Yeah, I don't like the general form. First thing I would do if I was me was turn it into the standard form and get the x minus h quantity squared stuff. Then I can know how to graph it. This, less useful. You're given this, you're likely going to change it into that, the standard form. So we're near the end of this section. Let's go through 3 more examples. I want us to find the standard form of the equation of a circle with center -3, 1 that's tangent to the y-axis. All right. I can graph it already. -3, 1, -3, 1, there's a center. It's tangent to the, it's a little typo there. It should read tangent to the x-axis. I wanted it tangent to the x-axis, so we'll get something like this in terms of the picture. Excuse me, I'll correct that typo. Based on this, we can go through and find the radius. You see that the radius must be 1. Radius must be 1. We've got the center, -3, 1. So we can write the standard form, x minus h squared plus y minus k squared equals r squared. Substituting in h equals -3, right? Be careful with the negative signs, hk up here. K equals 1, put a 1 in here. We know the radius is 1. We get a 1 squared on the right-hand side. And there you go. Given the information, sorry about the typo there, that should read an X to produce this picture at least, then we get this as the standard form for the equation of a circle. You're basically given the center, so that gives you the HK stuff, and you're given other information that produces the radius for the equation. Another one, an applied problem, if you like. Here's the statement of the problem as given in the book. It's it's got some extraneous information in it, as they sometimes do in these word problems. Opening in 2014 in Las Vegas, the high roller observation wheel has a maximum height of 550 feet and a diameter of 520 feet, with one full rotation taking approximately 30 minutes. Find an equation for the wheel if the center of the wheel is on the y-axis and the x-axis is at ground level. Okay. What it's called, where it is, and when they made it, irrelevant. We're looking for the equation for the wheel, the equation for the circle here, under certain conditions. The fact that it rotates and it takes some amount of time to rotate, irrelevant. We're looking for an equation for the wheel, the circle that corresponds to the wheel. If the center of the wheel is on the y-axis, so we'll introduce, here's a photo, we'll introduce a vertical y-axis and let the center of the wheel lie on that y-axis. And the x-axis is at ground level. So the x-axis will be somewhere down here. We'll draw a schematic of it on the next slide. The dimensions that do matter is the maximum height is 550 feet. So we'll have ground level down here. Maximum height on the wheel is up here. That distance from the ground to the top of the wheel, 550 feet. A diameter of the wheel is 520 feet. So distance from side to side, 520 feet. Distance from top to bottom, maybe more relevant, also 520 feet. So the pertinent information is the 550 feet, the 520 feet, and where the x and y axes are. So you got to turn those words into a picture, a schematic diagram. And let's use this. Here's ground level. Maximum height was 550 feet. If we center the wheel along the y-axis, there's a center of the wheel, as we've done. We get this to be 550 feet. You were told the diameter of the wheel was 520 feet. So if we'll take 550 feet, subtract 520 feet, you'll be left with 30 feet. And so the coordinate of this point at the bottom is 30 feet. We could also find the leftmost and rightmost points if you want. We know the radius is, well, we know the diameter is 520 feet. So based on that, we can find the radius and we could find these other points. Let's minimize what we do and answer the question they asked. So the average height of the wheel, just take this 550 feet above the ground and 30 feet above the ground, add those, 580 divided by 2 produces 290 feet. Looking for the midpoint, as we described it in section 1.1. The midpoint between these 2 points. Halfway between is 290 feet. So that's where the center of the wheel is. It had some, in the picture, it had some sort of supports. So schematically, I've drawn the supports in. That's not relevant to the equation. But do you believe those words turn into this picture? 550 feet gives you this point. The 520-foot diameter 520, produces a 30 feet here by subtracting, and we find the midpoint between those two, gives you that point. We know this is the center, so that allows us to sketch the circle out as something like this. Now they want an equation. Well, this would be a piece of cake. There's the center, HK, X is 0, X coordinate is 0, Y coordinate is 290, H is 0, K is 290. We know the diameter. From that, we can find the radius, and then we're in business. Center of the wheel is 0, 290, HK equals 0, 290, measured in feet. Radius is, if you like, we can measure the distance from here to here. 290 minus 30, 550 minus 290. If you like, we can measure the distance here. That's 260. Also, you could take the diameter, 520, and divide that by 2, and you're still going to get 260. Distance is measured in feet. So no matter how you slice it, the radius is 260, and we got 3 different ways to find it. Standard equation, x minus h, quantity squared, plus y minus k, quantity squared, equals r squared. we've got h is 0, k is 290, and r is 260. H, k, r, plug those in, produces this. Take 260 and square it if you like. I guess I get 67,600. And here's the equation of the circle describing the Ferris wheel in standard form. I can see the center is 0, 290, and we could take the square root of this to find the radius, or just leave it expressed like this, and you can see that the radius is 260 feet, everything measured in feet. Let's do one more. This one got a little more symbols in it, so it's more symbolic and less numerical, but you manipulate the symbols the same way you manipulate numbers. The story on this one is the tangent line to a circle may be defined as the line that intersects the circle in a single point, called the point of tangency. So we get something like this. Here's a circle, there's the line that's tangent to it, and there's the point of tangency. If the equation of the circle is x squared plus y squared equals r squared, that'd be a circle with center 0, 0, and radius r, center 0, 0. That's exactly what they've sketched out here. And if the equation of the tangent line is y equals mx plus b, here's the tangent line, and they're saying it's of the form y equals mx plus b. So where's the point of tangency? I don't know. What we've drawn here, we've got a point of tangency in the first quadrant, and we've got a tangent line that must have negative slope, goes downhill when read from left to right. Yeah, but if the point of tangency was over here somewhere in the second quadrant, then the tangent line would be something like this, and we'd have a positive slope. So again, this is just a schematic that illustrates what's going on, not to assume the point of tangency is in any particular quadrant. Also, by saying the tangent line is of the form y equals mx plus b, they're implying that the slope's defined, so it's not a vertical tangent line. So we'd have a vertical tangent line if the point of tangency was this rightmost point or this leftmost point. That must not be the case because they've told us to assume the tangent line has that form. Then they ask you to show some stuff. Show r squared times 1 plus m squared quantity equals b squared. So that's a relationship between these parameters, r, m, and b, the constants in the story. Give you a little hint, you're going to need the quadratic formula to do that. And this one's a little bit tricky. Even with a hint, it's a little bit tricky. The point of tangency, you're going to show that equals this in terms of r, m, and b. And you're going to show the tangent line is perpendicular to the line containing the center of the circle and the point of tangency. Center of the circle and point of tangency. This line, so just drawing the line segment, but the line that passes through these points, these two given points, is perpendicular to the tangent line. That's the third part. And you see that in high school geometry. I suspect it came up in Appendix A2, Geometry Essentials. Tangent lines are perpendicular to radii of circles. It's a result in Euclid's elements, so nothing new. But here we're going through and showing it algebraically using the stuff we know. Perpendicular, that's what product of the slopes is -1. So we'll have to deal with slopes in this. We know the slope of this line here, it's slope m. And I bet you we can find the slope of this thing here because we've got 2 points on that thing there. Given 2 points, rise over run, we can find the slope. So there's the question. Part A, show r squared times 1 plus m squared quantity equals b squared. Going to need the quadratic formula. Okay. At the point of tangency, x, y, we've got both x squared plus y squared equals r squared and y equals mx plus b. That one point lies both on the circle, and so its coordinates x, y satisfy this, and it lies on the line, and its coordinates satisfy that. So both of these hold at the point of tangency. So let's see if we can find some relationships between the constants based on the fact that both of these hold. Here's what we're going to do. Let's take the fact that y equals mx plus b and plug that in for y in this first equation. Substituting the second equation into the first equation gets x squared plus y squared, but y equals mx plus b. So we'll replace y with mx plus b squared equals r squared. Simply take this, plug it in there for y. Produces this. Can't argue with the validity of it and shouldn't argue with the logic of it. The point of tangency satisfies both of these, so that's a legitimate substitution. We now have an equation that's only got x's in it. That's a good thing. We've eliminated the y's using this relationship. What you're going to do next, I don't know, multiply this out because that's about all I see to do. So let's FOIL this mx plus b binomial squared. That'll produce first squared plus twice the product plus last squared. That'd be mx squared or m squared x squared. The product is mx times b, so we'll get two of those from the outer and the inner. And the last produces b squared. First squared, twice the product, last squared. Let's take the r squared to the left-hand side of the equation, giving us this. Now we've got a quadratic. It's got x squared terms and x terms and a bunch of constants. Set equal to 0. How about we collect together the x squared terms? So we got a 1 here and m squared there. So we'll have 1 plus m squared, x squared terms. X terms just here. So we'll have 2mb times x. And constants, we've got this. Put parentheses around the coefficients. We've got an x squared term with that coefficient, an x term with that coefficient. Here's the constant term, and this is set equal to 0. That's a quadratic equation, which we would solve using the quadratic formula. Solve using the, actually it should be quadratic formula to use the verbiage that our book uses. Quadratic formula says x equals negative b, where b represents the coefficient of x, right? Sorry about that. We've got the parameter b playing two different roles here. B in a y equals mx plus b role, and also it's not explicitly written anywhere, but verbally you think of b as the coefficient of x. The coefficient of x goes here, you know, b, but the coefficient of x here is 2mb. So substitute in the coefficient of x plus or minus the coefficient of x squared, you know, b squared, minus 4ac. I don't have any other a's and c's, so I don't feel bad about that. Minus 4a is the coefficient of x squared, that's 1 plus m squared. C is the constant term, that's b squared minus r squared. So b squared minus 4ac, quote unquote, produces this. Denominator is 2a, where a is the coefficient of x squared. So we can solve this for x symbolically as given using the quadratic equation. If that bugs you, pause it and make sure you believe we've put the right coefficients in the correct place. Produces this. In the picture, we saw there was exactly one x value satisfying this. There was only one point of tangency. A line can only be tangent to a circle at one point. Here, we're dealing with the x coordinate of the point of tangency. This better just give one x value. When is it that the quadratic equation produces a single real solution? Sometimes it produces two real solutions with a plus or minus. Sometimes it produces exactly one, that's the case we want. And sometimes it produces no real solutions. It's when you get negatives under the square root. It produces two complex solutions in that case. When is it we get a single value out for this? We get one value out when the discriminant is 0. See section A6 from the appendix, specifically it's note A.6.c, where we describe how many solutions you get in terms of the discriminant. We want exactly one solution from the geometry. There's only one point of tangency. So we need this discriminant to be 0. We need the plus or minus the square root of 0 so that we get a single x value. So we'll take the discriminant down here, set it equal to 0. You with me? Where are we going? Question was, show this. Okay, this is a relationship between M and B and R. Slope, intercept, radius of the line and circle under conversation. We've produced this. Well, that's all M, B's, and R's, so that's a good sign. Let's simplify it, and it ought to simplify to this. From this equation we have, okay, so we'll square this out. 2 squared is 4. We get an M squared and a B squared, doing the squaring. Let's FOIL this. We'll take care of the multiplication by -4 here in a second. We'll have first outer, see, that'd be these two. This is a -r squared, inner M squared, B squared, last M squared, -r squared, M squared, R squared, negative. FOIL it and it produces this. Let's see, does that simplify? It does. That'll give us a -4b squared, right? Plus 4r squared, right? Minus 4m squared b squared, but we got a plus 4m squared b squared out front. So this will cancel with -4 times this. That's gone. Both of those are gone. And -4 times -m squared r squared produces +4m squared r squared. And that's set equal to the right-hand side, which is 0. So it simplified down a bunch. What do you want to do next? Well, this ain't too complicated. I want to get this. Okay, so let's see if we can manipulate this and turn it into that. That ain't got any 4s in it. It's got a bunch of plus or minus 4s in it. So let's divide through by 4. If we divide by 4, that'll leave us with a -b squared, yeah, r squared, yeah, and m squared r squared. So get the 4s out of the way. You're still stuck with a negative out front. We're trying to match it up with this. Hey, we wanted a b squared on one side. Let's take this b squared to the right-hand side. That'll give us b squared on the right-hand side, as desired. Can we factor the other stuff? Can you factor an r squared out of this? You can. Factor r squared out of these two terms, and you're left with 1 plus m squared. And that's what you were trying to show. Why that is of interest is unclear. They wanted us to show it. There you go. So that's pretty tricky stuff. The fact that you would substitute in, that shouldn't be too much of a surprise, but that you would produce a quadratic, look at the quadratic equation, and observe from the geometry that there's only one solution to this. That's in my opinion, the trickiest part. But that's the way you do it, as in terms of the material previously described. Okay, so we've got that relationship. The real reason we've done that is to prove the next stuff. Part B says, show the point of tangency is xy equals this. So these are the coordinates of the point of tangency. Notice it involves R, M, and B again. Well, from part A, we just saw that we needed this relationship to hold. We needed the discriminant to equal 0. So we had this relationship, right? Can't argue with that. Why I would go looking at this is maybe a bit uninspired. You might not be able to come up with this too fast on your own, nor would I, probably not very fast. But you should believe we did this. We did this on the previous slide. So we had this relationship. This allows us then to deduce that x equals -2mb plus or minus, this whole thing was 0, plus or minus 0 over this. So we get for x, the point of tangency, equals -2mb plus or minus nothing, divided by 2, 1 plus m. We get this value for x without dealing with the plus or minus 0 stuff. So at the point of tangency, this is the case. We can cancel the 2's. That produces this. We're trying to get that. Well, we know more information. But at the point of tangency, x equals this. In part A, we had shown this. This was the conclusion of part A. Like I said, we did part A, so we can do this now. We know r squared times 1 plus m squared, quantity, equals b squared. Okay, then we could divide both sides by r squared to get 1 plus m squared equals b squared over r squared. Again, you can't argue with the validity of it. The motivation might not be too well established, but in this one, I'd be happy if you can just follow the manipulations. So let's take the 1 plus m squared here and replace it with b squared over r squared. Making that substitution, we'll have a b squared r squared in the denominator, negative mb in the numerator, x equals, make the substitution, negative mb in the numerator. We've replaced the 1 plus m squared with b squared r squared as promised. That produces this. It's got all m's, b's, and r's in it. Actually, it was all m's and b's earlier, so it looked like we needed to introduce the r's, and we've done that now. Compound fraction, we can take that r squared, move it to the numerator. We have to divide it by r squared, goes to the numerator as an r squared. There's the negative sign. We cancel this b with one of those. So b in the numerator is gone. We're left with a negative r squared m in the numerator. In the denominator, we had b squared. This is moved up, and we lost one of those to give a b in the denominator. And that's what you're supposed to get for the x coordinate of the point of tangency. So at the point of tangency, we have x equals this as required. How about the y coordinate? Well, the point also lies on the line. It also lies on the circle. Let's use the line. It's a simpler equation. We know y equals mx plus b. So at the point of tangency, which lies on this line, we have x equals this. So let's plug this in to that equation for x, and we'll get y in terms of m, b, and this, m, b, and r. And we'll have y in terms of m, b, and r. Interesting, there's no m there. We'll see what happens. Substituting in for x, this quantity, negative r squared m over b, produces this, y equals m, negative r squared m over b, plus b. Distribute, that'll give us negative r squared m squared. Pick up another m to produce an m squared. There's a b in the denominator. I tell you what, let's take this b and write it as b squared over b to get a common denominator so we can add those together. Can't argue with the validity of that as well. That allows us to add these together with a common denominator of b, producing negative r squared m squared plus b squared. Okay. In part A, we had seen that r squared times 1 plus m squared quantity equals b squared. So we can take y equals this quantity and do the following. Let's take this b squared and substitute in that. Not motivated, but certainly true. So we're going to replace this b squared with r squared quantity 1 plus m squared. Make that substitution. We get some simplification. Here we've got r squared times 1 plus r squared times m squared. There's a negative r squared times m squared. This negative rm squared, this negative r squared m squared will cancel with the r squared m squared here, leaving us simply with an r squared in the numerator and a b in the denominator. Whew, and that's what we wanted. So there's the y coordinate for the point of tangency, and we've shown what they asked us to show in part B. Not elegant stuff, but stuff you should be able to follow. Maybe not motivated stuff, but you should believe all these steps of algebra. And finally, really the goal of the question is to show that this line is perpendicular to that line. The tangent lines, y equals mx plus b. So its slope is m. The line containing the center of the circle and the point of tangency passes through the points 0, 0, that is the center of the circle, and the point of tangency, call it x2, y2. And we found in part B that this is the expression for the point of tangency. So we did part A so we could do part B. We did part B so we can do part C, really. Part C was the goal. 2 points on this line passing through the center and the point of tangency. I can find the slope. using 2 points, we'll take y2 minus y1, that would be r squared over b minus 0. x2 minus x1, that would be this thing minus 0, this thing minus 0. Drop the zeros and simplify. R squared over b in the numerator, negative r squared m over b in the denominator. The b's cancel, the r squares cancel, and they're in corresponding positions. And that leaves you with a negative and an m in the denominator. Leaves you with a 1 over negative m. So the slope of this line is negative 1 over m. That was fairly easy. What was hard was part A and part B. So we've got a line of slope m here and a line of slope negative 1 over m here. Well, you multiply those together and you get negative 1. Theorem 1.3.f says perpendicular lines have slopes whose product is negative 1. And when the product of the slopes is negative 1, then the lines are perpendicular. So that line and that line are perpendicular. Tangents to a circle are perpendicular to radii of the circle, or diameters of the circle, that pass through the point of tangency. A result from classical geometry, we've established it here using precalculus. Euclid would not establish it like this. He'd do it purely geometrically. We've done it algebraically using slopes and stuff that Descartes introduced 1700 years after Euclid. So there. And that completes chapter 1. So we'll move on now to chapter 2 and deal more with functions and graphs of functions. I'll see you there. Have a nice day.